Determinism versus emergence. On one hand, there have always been hints that the universe is inherently unpredictable, full of earthquakes and hurricanes and other acts of God. On the other hand, as Duncan Watts recently stated, we like deterministic stories, and, as Daniel Kahneman recently stated, stories about the past are so good that they create an illusion that life is understandable, that you can predict the future. Debates over determinism and emergence have raged within philosophy and science for thousands of years, and software engineering seems to be repeating those same debates as it evolves from waterfall to agile, from idealizing determinism and dismissing emergence to combining both. In the first section, we note that determinism and emergence are loosely coherent within themselves and completely incompatible with each other. We note that different contexts and different people naturally favor different concepts of reality. Everyone favors whichever concept gives them what they want. Increasingly, software engineers say do both, although nobody actually explains how to do so. Throughout most of the remaining sections, we delve into the individual facets of determinism and emergence as detailed by the rows of the table. In each section, we describe both ends of a facet and then argue that everyone needs both. And in the last section, we add some final notes. Bifurcated concepts of reality. The deterministic and emergent concepts of reality, or worldviews, are detailed in the columns of the table. They are both loosely coherent within themselves and completely incompatible with each other. Despite the looseness, we believe that the bifurcation sheds light on some of the conflicts within contemporary software engineering. For example, why some people love planning and others hate it. A wide variety of biases affect what people consider normal, what they aspire to, and how they actually respond in specific situations. Some biases come from contexts, such as tools and practices, and others come from roles, such as managers and programmers. All of these biases are completely natural and understandable. However, all of these biases can lead people astray. In the past, many idealists strove to impose whichever concept of reality they preferred on everyone else. Increasingly, pragmatists say, do both, even though nobody actually explains how to do so. Loosely coherent. Coherent. The facets of each concept of reality, the cells in each column in the table, act as loose metaphors for each other and reinforce each other. Within determinism, clockwork mechanics and rational behaviorism imply that physical objects and people are inherently predictable and controllable, and so metaphorically software projects should be too. Tools, rules, factories, and waterfalls fit together and reinforce each other because they all emphasize repetition of knowns, especially when writing machine-oriented programs such as embedded systems. Factories, scientific management, and reductionism all concern or require fixed sets of parts and tasks. Within emergence, quantum mechanics and irrational humanism imply that physical objects and people are inherently unpredictable and uncontrollable, and so metaphorically software projects should be too. Skills, judgments, artisanship, and agile fit together and reinforce each other because they all emphasize original responses to unknowns and surprises, especially when writing user-oriented programs such as games and social media. Workshops, lean management, and holism all tolerate evolving sets of parts and tasks. Loose. However, the facets of each concept of reality, the cells in each column, align imperfectly. We have found mismatches between every pair of facets that we looked at. Within determinism. Determinism differs from knowns because fractals can be both deterministic and impossible to predict. Determinism differs from reductionism because fractals can be deterministic as well as infinite. Some machine-oriented programs, such as operating systems, are enormous, complicated, and effectively emergent, and factory employees also use skills and judgments. Within emergence. Emergence differs from unknowns because electrons and photons move unpredictably, even though computers and networks use them to create determinism. Some user-oriented programs, such as business card apps for smartphones, are small and simple and effectively deterministic, and workshop employees also use tools and rules. Completely incompatible. Determinism and emergence seem completely incompatible, bicameral rather than spectral. We know of no ways to describe or understand either concept of reality in terms of the other. This bifurcation reminds us of the optical illusion shown in the figure. Each end makes sense in isolation, even though the whole figure is impossible. Flip sides of the same coin, good and evil twins. The ends of some facets begin at the same place and then head off in opposite directions. Statistics example. Both frequentist and Bayesian statistics start with the laws of probability, but each uses them in different ways to deduce different things. Frequentist statistics makes more sense when looking at the past, where lots of Gaussian data exists and it strives for objectivity. Bayesian statistics makes more sense when predicting the future, where little Gaussian data exists and it tolerates subjectivity. Program orientation example. All kinds of programs are built from similar lines of C or Java, but machine-oriented and user-oriented programs embody different ideals. Embedded systems and operating systems make machines more powerful, and they can endure as long as the underlying hardware endures, often for decades. Video games and social media make users more productive or entertained, and they are often fad-driven, sometimes enduring for a year or two at most. Having or knowing versus doing. The ends of some facets differ in the sense of having or knowing versus doing. Certification differs from skill. Knowledge example. Owning a tool differs from using a tool. For example, owning a piano differs from playing piano. Reading about a skill differs from practicing that skill. For example, reading biographies about pianists and books about music theory differs from practicing piano. Tools and practices example. Programmers use and read about a variety of tools and practices, including compilers, linters, coding standards, and inspections. Even so, writing lousy code in C and Java remains all too easy. Programmers must also develop and apply skills and judgments to write excellent and enduring code. Scale and composition. The ends of some facets differ by scale, especially when one is composed of the other. Mechanics example. Clockwork mechanics describe the predictable behaviors of large objects like cannonballs and planets. Quantum mechanics describe the unpredictable behaviors of small objects like electrons and photons. Large objects are composed of many, many small objects. Program description example. Most programs are composed of many algorithms, and scripts glue those algorithms together. However, the concepts and activities needed to create algorithms differ completely from those needed to create scripts. Algorithms embody mathematical truths that are objectively and deductively correct. They address common problems that can be studied and solved in isolation, and algorithmists share their results widely. Scripts embody user opinions that are subjectively and inductively correct at best. They solve situation-specific problems. Each project gets implemented once, and sponsoring organizations usually treat the results as private intellectual property. Degeneration. The ends of some facets differ in that one is a degenerate form of the other. Geometry example. Euclidean geometry can be thought of as a degenerate form of fractal geometry. Expansions with a kink of 0 degrees produce Euclidean spaces, while expansions with a kink of any other angle, such as 90 degrees, produce fractal spaces. Each geometry leads to a radically different understanding of what dimension and distance mean. Design example. Reductionism, where the whole equals the sum of the parts, can be viewed as a degenerate form of holism, where the whole differs from the sum of the parts. Each case enables and requires a different approach. Projects that easily decompose into parts and tasks can use deterministic waterfall and factory processes. Projects that do not easily decompose into parts and tasks need emergent, agile, and workshop processes. Visibility. The ends of some facets differ by their visibility. Deterministic concepts can usually be observed or experienced directly. Emergent concepts often remain invisible. Mechanics example. Seeing deterministic planets and cannonballs is much easier than seeing emergent electrons and photons. That sentence has an irony. Software example. Deterministic tools, rules, certifications, and contracts are much easier to see than emergent skills, judgments, expertise, drive, and relationships. When project statuses are visible and crisp, trust is unnecessary and waterfall and factory processes work well. When project statuses are invisible or murky, trust becomes essential and agile and workshop processes work better. Leap of faith. Accepting that invisible or emergent concepts exist often requires a leap of faith that not everyone willingly takes. From our position on the ground, the sun appears to move through the sky. Accepting that the Earth moves around the sun requires a leap of faith. Accepting that electrons and photons exist and move unpredictably requires a leap of faith. Accepting that Agile works better than Waterfall for many software projects requires a leap of faith. Unknown unknowns are invisible by definition, and accepting that they exist requires a leap of faith. Contextual biases. Different tools, practices, and ideals naturally favor different concepts of reality. Toward determinism. Program descriptions, tools, and practices. Program descriptions, tools, and practices favor determinism. Algorithms, tools, and rules are reliable and efficient when they work, but they don't always work. For example, no algorithms efficiently solve large NP-complete problems, and most programs are much larger, more arbitrary, and more complicated than any algorithm. IDEs help developers to write code, but IDEs cannot write code for developers. Developers should use deterministic or existing algorithms, tools, and rules whenever possible, and use emergent or new scripts, skills, and judgments as necessary. Planning. Planning favors determinism. Planning increases understanding and reduces risk when it works, but it doesn't work in the presence of unknowns. Projects should use plans and waterfalls whenever possible, and should use experiments and agile as necessary. Simplicity. Simplicity favors determinism. Transactional management based on contracts that exchanges work for money is simple and easy. Enlightened management that builds relationships remains vague and requires a lot of effort. So from a simplicity point of view, everyone should prefer work relationships to be as transactional as possible and as emergent as necessary. Productivity and quality. Productivity and quality favor determinism. When parts and tasks are fully known ahead of time, workers can prepare and then do the work quickly and correctly. So from productivity and quality perspectives, everyone should prefer work to be as deterministic or as known as possible, and as emergent or unknown as necessary. Toward emergence. Motivation. Motivation favors emergence. People respond much better to peers and clients than to managers, and they do much better work with enlightened management. Transactions and contracts that trade work for money actually demotivate most workers. Even so, workers still need salaries and project assignments. So from a motivation perspective, everyone should prefer work relationships to be as enlightened as possible and as transactional as necessary. Role biases. Different roles naturally favor different concepts of reality. Toward determinism. Purchasing managers. Purchasing managers who spend money, often millions of dollars or more, on software projects would prefer to spend less. They would prefer to buy software once and never again. They naturally want guarantees about results, about cost, quality, and deliverables. Project managers. Project managers naturally want to set accurate expectations about goals, budgets, schedules, and deliverables up front, and they want to minimize the changes and errors that will occur throughout the project. They want to increase transparency and objectivity, as well as to decrease hand-waving and guessing. Architects. In order to accelerate the progress on projects and to predict and control the evolution of programs, designers want to create enduring software architectures. Educators and students. Certifications test for specific knowledge. Educators want to teach to the test, and students want to study for the test. So both educators and students want stable, bounded bodies of knowledge. The committee members who write standards for education, like Sweebach, want them to be complete and enduring. Regulators. Regulators at the FAA and FDA naturally want aerospace and medical software to be perfect. Psychologists have shown that obsessing over perfection or minimizing mistakes leads to a fixed mindset that emphasizes states of being. Many of these individuals are high-status authorities who personify projects, organizations, and ideals. They naturally want to be able to predict the future, to control projects, and to minimize changes and errors. They tend to idealize stability and outcomes, specifically finished programs. They want software engineering to be bounded and deterministic. Emergence contradicts their heartfelt desires. Toward emergence. Programmers. Programmers write features and fix bugs day by day, so they create emergence day by day. When working on upgrades, they naturally want to make their marks on those programs, so they naturally argue that architectures must change. They want to increase the value of their individual experiences, skills, and judgments, and they want ongoing opportunities to write new programs that will affect the world. Researchers. Researchers want to think about software in new ways, so they want new concepts within software engineering to arise continually. Many of these individuals are low-status workers who actually do stuff. They naturally want change to occur continually. They tend to idealize possibility and opportunities to write the programs of the future. They want software engineering to be unbounded and emergent. Determinism contradicts their heartfelt desires. Historically, idealists tried to impose their preferences on everyone else. We would like to urge everyone, managers and developers alike, to see the world as it is and to embrace the full spectrum of possibility of what could or should happen during a project. But doing so asks for way too much. Psychologists have shown that heartfelt desires influence rational thought, which is called the self-serving bias. People naturally favor the concepts of reality that will give them what they want, based on their circumstances and worldviews, regardless of what the situation calls for, regardless of what they might otherwise rationally believe. Everyone naturally sees what they want or expect to see. They tend to be unaware of their own biases and oblivious to everyone else's needs. As long as nobody gets carried away, all of the biases listed above really are just fine. In fact, everyone really should want what they want. Questions like how to lower the cost and raise the quality of software programs are useful and important. Questions like what are the programs and technologies of the future are also useful and important. Someone needs to work on cost and quality, and someone else needs to write new programs. Unfortunately, fans of one worldview often act as if their concept of reality will work for everyone else too, and they tend to dismiss all other worldviews whenever it suits their purposes. Over the past 30-some-odd years, the IEEE and the SEI have advocated for deterministic practices like CMM and SCAMPI, certifications like PSP and CSDP, and standards like SWBOC. Over the past 20-some-odd years, we, the authors, have advocated for emergent practices like Agile, improvisation, and subjective judgment like the chaos model and chaos strategy. But software engineering really is much larger than either side alone. Today, pragmatists say do both, even though nobody says how. Everyone actually needs both. We have come to believe that everyone needs both determinism and emergence, and that everyone already mixes them naturally, if ad hocly. In our experience, all projects and most tasks combine determinism, knowns, and emergence, unknowns. Toward emergence. Most projects have some core functionality that is known precisely up front. Projects to write embedded systems and operating systems obviously emphasize determinism. However, projects to write video games and social media also have machine-oriented tasks that emphasize determinism, such as improving performance via better algorithms and query optimization, or accessing new data sources via translation of representations. Toward emergence. Most projects have many unknowns and encounter many surprises. Projects to write cool video games and social media that respond to the whims of users obviously emphasize emergence. However, projects to write low-level operating systems and embedded systems often have tasks that emphasize emergence. Users routinely think of new features, and most low-level programs must get some information out to users at some point, so developers must also improve user interfaces with better information controls and dashboards. More and more pragmatists encourage both. More and more software engineers urge everyone to use both concepts of reality. However, saying use both is easy, while effectively doing so remains hard. The ends of each facet mix more like a tossed salad than like a roux or gravy. We don't know of anyone who explains how to synthesize or unify both ends of any facet into a coherent whole, and we now suspect that nobody will ever do so. Regardless of what anyone aspires to do in any given situation, it seems that he or she must actually use one extreme or the other. Mechanics example. Nearly a century after physicists understood both relativity and quantum mechanics, they continue to use each theory independently. Stephen Hawking combined both theories to explain how black holes evaporate, but even so, no well-accepted theory of quantum gravity exists. Statistics example. In the 1980s, Joe Hill helped to unify frequentist and Bayesian statistics into empirical Bayes. Hill described empirical Bayes with, quote, be as frequentist as you can and as Bayesian as you must, which, alas, still really means doing one or the other. Boehm and Turner example. Barry Boehm and Richard Turner wrote about combining agility and discipline, but in every example they ended up arguing for either one or the other at a broad brush level. For example, they wrote that everyone should scale Agile by doing more planning, so they still advocate doing one or the other. We note that they use the term balance rather than synthesis, suggesting that they understood the difficulty of combining them. Safe example. Scaled Agile Framework, or SAFe, combines both determinism and emergence. Principle 4 is Agile, or the emergent bottom-up work that developers do. Principle 5 is Milestones, or the deterministic top-down planning that managers do. So SAFe says do both Agile and Waterfall, but it doesn't actually say how to combine them. Less example. Large-scale Scrum, or LESS, says do both systems thinking and lean thinking, both managing and coaching, both architecture and structure, and continuous improvement. So LESS says do both determinism and emergence at a finer grain, but it still doesn't actually say how to combine them. Larman and Vode example. Craig Larman and Bas Vode argued that gymnasts and Navy SEALs are both agile and disciplined, and so synthesis might seem possible. We totally agree with their point, but in their example, agility and discipline actually occur on independent dimensions and so remain distinct rather than unified concepts. The author's example. Throughout this chapter, we, the authors, urge software engineers to use both determinism and emergence appropriately. We now believe that determinism and emergence should matter equally, half and half more or less. Unfortunately, we cannot describe how to synthesize both ends of any facet into a coherent, unified whole because we haven't figured out how to do so. Doing both ends together half and half is a reasonable start. Combining both determinism and emergence means mixing them, person by person, task by task, detail by detail, as appropriate to each specific situation. Choices matter because the approach that actually handles each task affects expectations about planning, control, optimization, and outcomes. Philosophy. Determinism. People have always wanted to predict and control their fates, and they have always striven to overcome the randomness of the world. Their desires for a deterministic universe are natural and will never end. In particular, those with wealth or status won't want to lose the advantages that they have gained. In a deterministic world, everything can be known, so surprises should never occur. In a deterministic world, smart and attentive people can predict the future even when it isn't easy. They shouldn't have to handle cases that they don't know about because such cases should not exist. Surprises mean that someone didn't pay close enough attention or didn't think hard enough. Statisticians can analyze known existing data using frequentism because the future merely repeats the past. Software examples. Many software problems today have deterministic solutions, specifically those that are solved by existing algorithms, tools, and practices. In particular, many small, embedded signal processing, DSP, cryptography, and network programs have deterministic solutions, especially when someone can write a code generator or compiler for it. Computers provide stable platforms for programs, and programs extend computers. The small machine-oriented, algorithm-based, tool-based, and practice-based parts of projects are often deterministic. History. Ancient China. Around 2,500 years ago, some Chinese philosophers emphasized determinism and rules. Confucius developed rituals to respond to the situations that arose repeatedly in everyday life. For example, greeting friends or playing songs on flutes, and in government, resolving disputes between neighbors. Practicing rituals makes them natural and easy. Confucius said, quote, "If you don't know Li, or rituals, you cannot take your stand." Mencius refined that philosophy, saying, quote, "There is nothing that is not destined." Han Feizi and other legalists attempted to impose fa, or rules or patterns, on the world. Ancient Greece. Around 2,300 years ago, some Greek philosophers emphasized determinism. Zeno of Citium founded Stoicism, saying, quote, "Fate is the endless chain of causation." Cicero expressed Stoic principles, saying, quote, "All things happen through antecedent causes." Both men were wealthy and had every reason to want to sustain the status quo. At the time, both China and Greece were becoming literary societies, but lots of things remained unwritten. Drill and ritual remained essential to acting consistently, whether hanging out with friends or working in the government. Ancients used drills and rituals, where moderns might use training manuals and checklists. Newtonian mechanics. Around 300 years ago, during the Enlightenment, Newtonian mechanics inspired a new wave of deterministic philosophy. Clockwork mechanics suggested that predicting the future is possible, and as a consequence, accurately predicting and controlling the future are also possible. Computation. The first generations of electronic computers from the 1940s through the 1970s inspired another wave of deterministic philosophy. Almost everything that can be reliably solved by computers, algorithms, and programs is deterministic, though there are also a variety of probabilistic and heuristic techniques. One could even argue that computer science is the study of what can be known or achieved deterministically. Computation seems to have inspired governments and businesses to emphasize deterministic processes for workers and customers. Popular culture examples. Determinism has become enshrined in popular culture. For example, in 2017, Sherlock Holmes said, quote, "I have theorized before that if one could attenuate to every available data stream in the world simultaneously, it would be possible to anticipate and deduce almost anything." Late 20th century Americans tend to believe that they are, or should be, in control of their fates. Emergence. Emergence has been around forever. Humans have always dealt with whatever random events actually happen, even when they don't want to or like to. Nobody has ever been able to reliably predict the future out very far. Nobody has yet been able to prevent the world from changing for very long. In an emergent world, the future will continue to change in unpredictable and surprising ways, and it will increasingly diverge from the past. The future will routinely surprise even the smartest and most attentive people. When changes occur, data and models about the past will lead everyone astray, so statisticians can only predict the future using Bayesian approaches. Social change examples. Scientists, product developers, entrepreneurs, and social activists all attempt to do things that have never been done before, to do the unexpected or innovative. They all attempt to reveal previously unknown opportunities and then to change the expectations and behaviors of people in society. Technologists don't try to change society directly, but books, electricity, cars, and smartphones have affected society profoundly. Entrepreneurs do not use the past to predict the future. They fail until they succeed. Software examples. To the extent that any program was not predicted in the past, it embodies emergence. Every software project deliberately tries to create chunks of change or emergence that benefit the sponsoring organization. Software has always had emergent, user-oriented artisan niches, for example, in new markets and in research. User-oriented software is annoyingly emergent because whenever users see a finished program, they raise their expectations and move the goals again. Users will continue changing their minds and asking for more and better features for the foreseeable future. Terminology. Philosophers prefer the term indeterminism to contrast with determinism. But that term is consistent with purely random change, where positive and negative changes can occur more or less equally and cancel each other out. Software engineering seems to have some form of ratchet based on comparison or learning that drives the field in a positive direction, so we prefer the term emergence. Free will. Emergence in philosophy is usually associated with free will. In a deterministic world, nobody would actually need to live their lives out to find out what will happen. So emergence makes living each life out essential. History. Ancient China. Around 2,500 years ago, some Chinese philosophers emphasized emergence. Lao Tzu advised responding to change, saying, quote, "Life is a series of natural and spontaneous changes. Let things flow naturally." Chuang-Tzu refined that philosophy, saying, quote, "Flow with whatever is happening. Let your mind be free." Each encouraged people to appropriately accept and respond to the surprises that inevitably arise. Ancient Greece. Around 2,300 years ago, some Greek philosophers emphasized chance and change. Aristotle discussed emergence, saying, quote, "Fortune and chance are said to be in the number of causes." Quantum mechanics. Nearly 100 years ago, quantum mechanics inspired a new wave of emergent philosophy. In 1931, only a handful of years after the uncertainty principle was defined, Arthur Compton suggested that predicting the future is impossible, and so the best anyone can do is to respond as the future unfolds. Both. In general, software engineers need both some determinism and some emergence. In a world with some of each, software often merits writing, but few guarantees exist. A combined world is neither fully determined nor fully random. Determinism. If the world were totally random, without stability, then nothing could ever be planned or built because doing so would provide no advantages, and the only ways to succeed would stem from luck. Without a reasonably stable foundation on which to predict the future, nobody would ever invest in new software. Emergence. If the world were purely deterministic, predicting the future based on the past would be possible, and so there would be no unforeseen changes, no surprises, no new opportunities. The first mover or the biggest, richest organization would always win. All attempts to change the status quo would easily be predicted and thwarted, and the status quo would continue forever. Without some emergence, writing new software would make no meaningful difference, so nobody would bother. Mechanics. Clockwork. Ever since Copernicus, Kepler, and Newton sparked the scientific revolution, researchers have been trying to make nature predictable in earnest. David Hand notes that between the 17th and 20th centuries, scientists discovered the deterministic laws of nature. The improving clockwork mechanics made nature appear increasingly predictable. By using Newton's laws, Maxwell's equations, and other rules, one can predict and even manipulate nature. According to Newtonian science, nothing is unpredictable in principle. In 1814, Pierre-Simon Laplace wrote that if a supreme intelligence could know the position and velocity of all particles accurately enough, it could predict the future. This supreme intelligence, known as Laplace's demon, became the mascot for scientific determinism. The main limit to knowledge about the future is the precision of measurements, and whoever can measure their reality accurately enough will predict their fates. In 1943, Albert Einstein famously argued God does not play dice. History. In the 300s BC, Aristotle believed that the Earth was the center of the universe and that the Sun and planets orbited the Earth. Most Europeans accepted this theory as scientific truth for nearly 2 millennia. In 1543, Nicolaus Copernicus's De Revolutionibus Orbium Coelestium was published, which explained the heliocentric model of the planets. His model unified the motion of the Sun with the seasons and provided a foundation for the Gregorian calendar. Between 1615 and 1621, Johannes Kepler's Epitome Astronomiae Copernicani was published, which described the elliptical orbits of the planets. In 1687, Isaac Newton's Philosophiae Naturalis Principia Mathematica was published, which unified the motion of heavenly and terrestrial bodies, specifically planets and cannonballs. In 1915, Albert Einstein published the General Theory of Relativity, which refined Newton's equations. Quantum. Quantum mechanics has been undermining determinism ever since the late 1920s. Two important phenomena are Heisenberg's uncertainty principle and particle wave duality. The first states that nobody can know the position and momentum of a particle to an accuracy greater than Planck's constant, which explicitly limits what Laplace's demon can know. The second states that electrons behave like particles when observed as particles and like waves when observed as waves. Both phenomena imply that particles move unpredictably, at least part of the time. Quantum effects are tiny, mostly contained within atoms, so originally they were ignored in the macro world. More recently, scientists have shown particle wave duality for objects with the mass of 10,000 hydrogen atoms. Even cows would exhibit particle wave duality if one could build large enough accelerators. When combined with the butterfly effect, that under the right conditions the flap of a butterfly wing can cause a hurricane, the uncertainty caused by quantum mechanics can escape into the macro world and affect us all. So at its core, the universe is unpredictable and emergent. History. In 1877, Ludwig Boltzmann suggested that physical systems, later called molecules, have discrete levels of energy. In 1897, Joseph Thomson discovered the electron. In 1900, Max Planck solved blackbody radiation by presuming that energy is released in quantized packets. In 1905, Albert Einstein argued that energy quanta, later called photons, are absorbed and generated as holes. In 1923, Louis de Broglie proposed that particles can behave like waves and vice versa, which Clifton Davison and Lester Gerner showed experimentally in 1927. And in 1927, Werner Heisenberg proposed the uncertainty principle. Both. In general, software engineers need both clockwork and quantum mechanics. Clockwork. All of the clockwork mechanics remain valid today. The concept of day remains geocentric and Aristotelian. Scheduling an appointment with a colleague about a software project for next week concerns the motion of the sun through the sky. The concept of year remains heliocentric and essentially Copernican. Tossing a ball to a dog remains Newtonian. Quantum. All contemporary high-speed computers and networks tame electrons and photons. Statistics. Frequentist. Determinism in science depends on probability and especially on frequentist statistics. David Hand notes that randomness seems incompatible with determinism, but they complement each other and they evolve together. Quote, "The idea that chance could be quantified arose at the same time as the view that the universe was intrinsically deterministic. Determinists needed a rug to sweep the messiness of nature under, and probability is that rug." Software examples. Many people believe that they can understand all questions by gathering and analyzing a lot of data, and that when they have gathered a lot of data, useful information must exist. These beliefs provide rationales for aggregating large databases of software projects or consumer purchases and then using machine learning. Such efforts routinely uncover useful insights. History. Classical statistics. Classical statistics concerns gambling and emphasizes crisply defined games of chance, such as those based on cards or dice. Around 1564, Girolamo Cardano wrote Liber de Ludo Alle, which for the first time correctly defined odds. In 1654, Pierre de Fermat and Blaise Pascal exchanged letters solving the problem of points and defining the expected value of an incomplete game. In 1657, Christian Huygens published De Ratiocinis in Ludo Alle, the first treatise on probability. In 1713, Jacob Bernoulli published Ars Conjectandi, which proved the law of large numbers. And in 1812, Pierre-Simon Laplace published Théorie analytique des probabilités, the second treatise, which defined the field of probability. Frequentist statistics. In the early 1900s, Ronald Fisher developed analysis of variance and hypothesis testing, which formed the basis of frequentist statistics. In frequentism, models come from the data. For example, an average and a standard deviation can describe a set of data points. When statisticians gather enough Gaussian data, meaning that the law of large numbers applies, frequentist models are simple and strong. Bayesian. Statisticians know that data and models are often incomplete and that frequentists cannot predict anything that remains absent from the data or the model. For example, frequentists cannot predict anything about a series of events before the first event has occurred, before they have sampled enough events for a valid model, or when the data is not Gaussian. Bayesian models can express rational uncertainties about a much wider range of situations than frequentist models can. For example, Bayesian belief networks can support rational decisions when one lacks enough data for valid frequentist models. Bayesian deductions span the gamut from purely subjective to purely objective by combining arbitrary priors, personal opinions, and empirical samples. When nobody knows anything about the actual probability of an event, one can start by presuming it is 50-50 or 1 over n. Whenever someone believes that he or she has a better personal opinion or subjective estimate, he or she can use that. When someone has objective data, he or she should use that. Bayes' law shows how to incrementally improve models as better evidence becomes available. Innovation. It has been argued that all innovation requires a Bayesian point of view, because valid frequentist models simply don't exist until after an experiment has been repeated many times. Requiring a valid frequentist model before doing anything new precludes ever doing anything new. For example, valid frequentist models of how a new product will sell in the market don't exist because one can only gather such data and develop such models after the product already sells in the market. Note that if big data and frequentists could discover everything worth learning, scientific research would be unnecessary. Note also that Bayesian statistics can analyze known Gaussian data. History. In 1763, Richard Price published Thomas Bayes' paper about inverse probability, or reasoning from effect to cause. Then everyone totally ignored it for a century, and then mostly ignored it for another century. Computation. Sharon Birch McGrain argued that computation explains why Bayesian statistics did not break through until the 1980s. Bayesian models are usually much larger than frequentist models, so updating Bayesian models requires a lot more computation. When computations were done by hand, meaning slow and error-prone, small frequentist models were the best that anyone could reliably compute in practice. As inexpensive computers became available in the 1970s and 80s, Bayesian statistics took off. Arbitrary and subjective. Many people, and especially frequentists, disdain the arbitrary and subjective elements of Bayesian statistics. Frequentists disparaged subjectivity throughout most of the 1900s. However, various mavericks championed Bayesian statistics off and on for over a century, including Vilfredo Pareto, Richard Price, Frank Ramsey, Bruno De Finetti, Richard Jeffries, Irving Good, and Leonard Savage. Both. In general, software engineers need both frequentist and Bayesian statistics. The following example is absurd but suggestive. Consider a company that wants to develop a new consumer product, one out of the enormous possibilities. Frequentism. Frequentist models better predict the past. Frequentist statistics can reveal how the experiments turn out or how the product actually performs in the market. Bayesian. Bayesian models better predict the future. Bayesian statistics can use opinions and incomplete data to decide which experiments to run or which products to prototype. Statistics is a modest technique for seeing the invisible, which is why so many managers love metrics. But laymen are remarkably superstitious about statistics because it can only reveal limited aspects about the future. Geometry. Euclidean. Math was initially developed to understand the past and predict the future. Accountants want to add up bills in restaurants and stores in the same predictable ways. Bankers want to reliably compute compound interest. Soldiers want to reliably compute the arcs of cannonballs. Euclidean geometry concerns the relationships between independent dimensions. In Euclidean geometry, dimensions are separate and they scale in the ways that one learns in high school classes. Fractal. There are many non-Euclidean geometries, but fractal geometry is particularly interesting. The complexity, catastrophe, and bifurcation theories explain how tiny differences in initial conditions and paths can affect outcomes. Butterfly effect. Perhaps the best-known example of complexity theory is the butterfly effect. Most butterflies don't affect the atmosphere whatsoever, but under the right conditions, the flap of a butterfly wing can cause a hurricane. This resembles the, quote, "for want of a nail, the war was lost" proverb. Most nails have no effect on the outcome of any war whatsoever, but on rare occasions, under the right conditions, a nail can change the course of history. Living plants and animals, as well as electromechanical systems, can all amplify change, whether random or deliberate, to foster emergence. Initial conditions and unpredictable outcomes. Complex systems that are purely deterministic can appear either completely predictable or completely random, or anything in between, depending on the initial conditions. Big differences in initial conditions can lead to essentially identical outcomes. Minuscule differences in initial conditions can lead to radically different outcomes. Lorenz's strange attractor, Feigenbaum's logistic map, and Mandelbrot's set all show that some initial conditions produce predictable results and others produce seemingly random results. Any error in the measurement of initial conditions, no matter how small, can potentially grow to overwhelm the signal. Paths and unpredictable outcomes. Complex systems that contain any randomness or variations in paths can appear totally predictable or totally random or anything in between, depending on the sequences of events or actions. Bifurcation theory provides models where some sequences of events lead to predictable results and other similar sequences don't. The swallowtail cusp and butterfly equations from catastrophe theory show this sensitivity to paths. Everyday games like chess and Go do so too. The rules are very simple, yet the games are very complicated. There are many ways to win and many ways to lose. Some moves will change an outcome significantly and others won't. Minute variations in a path may or may not matter, and few people play either game well. Complexity may or may not undermine induction. Herbert Simon noted that for some systems, complexity may be manageable. For example, all airplanes manage the turbulence of air during flight. On the other hand, for other systems, understanding chaos does not give one the ability to predict. Sensitivities to initial conditions or paths and the resulting differences in outcomes can show up either quickly or after a long time, which undermines induction and predicting the future based on the past. Since only perfect measurements of a complex system can reliably predict the future, nobody can trust finite sequences of empirical measurement to reveal truth. Stability in complex systems can lull people into false confidences. Mechanics example. Most orbits of a planet like Mercury are stable. But for perhaps 1% of the orbits, the planet will move predictably for billions of years, and then crash into the sun or into another planet against all prior expectations. Software examples. In numerical computations, round-off errors can either cancel each other out or accumulate and overwhelm computations. Software architects often discuss, quote, the set of decisions that are hard to change. Every argument that architects should do big design up front to avoid problems later implies that those parts of software projects are sensitive to initial conditions. Barry Bame's Kokomo equation and the concept of diseconomy of scale are also fractals. History. The public became aware of fractals and chaos theory in 1982 when Benoit Mandelbrot published The Fractal Geometry of Nature, which contained many pretty pictures. Mandelbrot documented examples from hundreds of years in math, physics, biology, economics, meteorology, and the arts. Math example. In the late 1600s, Gottfried Leibniz noticed the self-similarities of line segments, but didn't know how to generalize the observation. In 1890, Giuseppe Peano showed the first of the monster curves, lines that could interleave dimensions to fill planes and volumes. The traditional concept of physical dimension became amorphous, and the differences between lines, planes, and volumes became murky. In the 1970s, Mitchell Feigenbaum developed his logistic map, and Benoit Mandelbrot developed his set. Three-body example. In the mid-1890s, Henri Poincaré became possibly the first to understand chaos theory when he solved the three-body problem. The two-body problem, for example, the Sun and the Earth, can be solved easily. The three-body problem, for example, the Sun, the Earth, and the Moon, may or may not be solvable. Some initial conditions lead to predictable outcomes, and others lead to seemingly random outcomes. Turbulence example. In 1963, Edward Lorenz published Deterministic Non-Periodic Flow, describing his strange attractor, which models turbulence in the atmosphere, dynamos, and motors. Brownian motion example. Small particles in calm air or liquid move in jagged curves called Brownian motion. These curves have been studied for millennia, from Lucretius in 60 BC to Jan Egginghaus in 1785 to Robert Brown in 1827 to Albert Einstein in 1905. Biology example. Many biological systems have fractal shapes, including the shapes of lungs, the shapes of circulatory systems, the shapes of trees, the locations of trees and forests, predator-prey cycles, and on and on. Both. In general, software engineers need both Euclidean and fractal geometries. In our experience, most software projects include both some independent or new features as well as some interdependent or improved features. Figure 2 contrasts 4 expansions of Euclidean and fractal, or dragon, curves, which model these features. Euclidean. Each Euclidean expansion goes twice as far as the previous one. Euclidean curves model going further to get more independent or new features, in other words, to get more productivity. Fractal. Each fractal expansion goes from the same starting point to the same ending point by a route that is twice as intricate. Fractal curves model going deeper to get interdependent or improved features, in other words, to get higher quality. Every feature could always be better. Refining each part of a program by one level doubles the cost of the whole program, so quality is anything but free. Knowledge. Bounded. For most of human history, knowledge was bounded because good, generalizable information was hard to acquire and expensive to share. Before the printing press, scholars shared knowledge through lectures and handwritten scrolls. People had to live in cities with academies and libraries, like Athens, Alexandria, Fez, or Bologna, to become educated. Very few people had the opportunity, time and resources, to do so. Only after the printing press could encyclopedias cost-effectively document and share large swaths of knowledge. In a bounded world, all important knowledge can be captured and expressed in encyclopedias. Encyclopedism. Bounded. In a bounded world, encyclopedias can describe the truth, the whole truth, and nothing but the truth. When knowledge is effectively finite and innumerable, encyclopedias work. Due to the difficulties and costs of gathering knowledge and printing it, encyclopedias had to be bounded. Gatekeepers. Because of the cost of generating and sharing knowledge, gatekeepers controlled the flow of resources and therefore the flow of knowledge within society. Experts wrote articles and acted as gatekeepers for what gets shared. They tend to prefer conservative information that will remain stable for longer. Software examples. Mary Shaw recently argued that menus in a website can describe all relevant software architectures. The IEEE claims that SWBOC describes everything that anyone needs to know about software engineering. Editors and committees at SIGSOFT and TCSE act as gatekeepers for the software engineering community. History. In the 300s BC, Aristotle developed an early compendium of human knowledge about physics, biology, math, and so on. It was not called an encyclopedia because that term referred to the knowledge needed for a general education. The first book titled Encyclopedia was published in 1559 by Pavo Skalik. The first books to embody the modern notion of compendium of all knowledge were Cyclopedia by Ephraim Chambers in 1728 and Cyclopedia by Denis Diderot and Jean Leronde d'Alembert in 1751. More recently, Encyclopedia Britannica and then Wikipedia have taken over as the repositories of all that anyone needs to know. Deduction. Deduction enables people to generalize and make full use of existing knowledge. The ancient Greeks were among the first, who we know about, to aspire to perfect rational human discourse. They developed rhetoric and simple rules of inference like modus ponens and modus tollens. In the late 1600s, Gottfried Wilhelm Leibniz wanted to resolve human conflicts using logical deduction, famously writing "Calculemus" or "Let us calculate." He developed an early propositional calculus and a knowledge representation scheme. In 1854, George Bull published the Laws of Thought, which described a complete propositional logic. In 1879, Gottlob Frege published Begriffsschrift, which described logical quantifiers. Making math rigorous turned out to be much easier than making human discourse rigorous. Between 1910 and 1913, Bertrand Russell and Alfred Whitehead published Principia Mathematica, which formally derived set theory and arithmetic. They combined Gottlob Frege's logic, Giuseppe Peano's axioms from 1889, and the new type system to remove paradoxes. Throughout the 20th century, mathematicians sought to deterministically evaluate the truth of all expressions and to enumerate all of math and to make it rigorous. The drive for completeness and rigor eventually led to mechanical proof checkers. Matty Tedder argued that verificationism nearly fulfilled Leibniz's dream. Donald Knuth documented ongoing progress in knowledge representation using Boolean logic and deduction using satisfiability solvers. Unbounded. In recent years, the infinite and error-laden nature of human knowledge has become better understood. In an unbounded world, knowledge is too large for any person or group of people to understand everything. Encyclopedias simply cannot describe everything that one needs to know, and deduction cannot fill in all of the gaps. The glut of fake news exacerbates these problems. So every year, all encyclopedias become more overwhelming, more incomplete, and more error-laden. In an unbounded world, many things remain unknown. A lot of important knowledge has not yet and never will be expressed. Anti-encyclopedism. Infinite. In an unbounded world, encyclopedias are finite approximations of the infinite and evolving truth. In Too Big to Know, David Weinberg shows that way too much information exists for anyone or any group to know everything, and so knowledge has become effectively infinite. In particular, the Internet contains so much information that it overwhelms everyone. Error-laden. In The Half-Life of Facts, Samuel Arbesman showed that knowledge expires in predictable patterns, much like radioactive decay, even when the expirations of individual facts remain unpredictable. In general, half of all scientific papers expire within a couple years, and half of all scientific books expire within a decade. This notion was originally published by the IEEE. Encyclopedias have the same problems. Some ideas are not yet expressed articulately. Some ideas are wrong and should be deleted. Many ideas are off by a bit and should be refined. The problem is that nobody knows what and where the problems are, i.e., can distinguish between which ideas are right and which are wrong. If anyone did know, they would just fix the problems. So editors must continually maintain encyclopedias to keep them up to date as understanding improves. No gatekeepers. Fake information has been around for a long time. There has always been propaganda. In the 1960s, Trural and Kaplauschus defeated Pirate Pug using a random information generator. The Internet has few gatekeepers, which allows everyone to share new information, but it also allows them to share fake information. Distinguishing between real and fake information is hard, in part because fake news often tells people what they want to hear, while real news often tells people what they don't want to hear. On the web, fake information can easily undermine or drown out real information. History. Awareness of the limits of human knowledge has been around for a long time. In 1887, Sherlock Holmes said, quote, "There comes a time when for every addition of knowledge you forget something that you knew before. It is of the highest importance, therefore, not to have useless facts elbowing out the useful ones." In 1972, Edgar Dijkstra wrote a chapter in Structured Programming about the limits of the human brain, titled On Our Inability to Do Much. In 2005, Niklaus Wirth wrote about the limits of intellectual capability in regard to the design of Modula 2 and Oberon. Anti-deduction. The ancient Greeks knew that the square root of 2 is irrational and cannot be written out, even though it can be constructed using ideal calipers and straight edges. But for millennia, that limitation mainly concerned precision, and knowing all other mathematical truths seemed possible. Incompleteness. In 1931, Kurt Gödel showed that nobody can know everything that is true in mathematics. In 1936, Alonzo Church and Alan Turing independently showed that nobody can solve the halting problem. For the first time, mathematicians became aware of specific hard limits to mathematical deduction. Intractability. In the early 1970s, Stephen Cook and Richard Karp showed that many well-defined problems like satisfiability and traveling salesman are incomplete. Nobody knows how to solve the general cases of these problems without exponential algorithms. Most likely, many additional problems exist that will remain unsolvable for other reasons or are less crisply defined. Truth emerges slowly because mathematicians and computer scientists can always discover more and more truths, yet nobody can ever know them all. Matty Tedder argued that formal verification ran out of steam in the 1980s and that software engineering stepped in to fill the void. Tedder noted that math differs from programming and that computers differ from the real world and that the physical world is uncertain. Daniel Jackson and Mandana Vaziri gave verificationism another boost in the early 2000s by harnessing the rapidly improving satisfiability solvers. But verification seems to have lapsed again since then. Both. In general, software engineers need both bounded and unbounded concepts of knowledge. Bounded. Software engineers know a lot of algorithms, tools, and practices. Sweebach documents a useful baseline of knowledge that practitioners should start with. Unbounded. If software engineering were bounded, then programmers would eventually write the last program, and a standard committee could just enumerate them all and close the profession. In an unbounded world, new software problems and new software technologies will continue to arise forever. Motivation. Rational behaviorism. Rational. When John von Neumann founded economic game theory in 1944, he treated people as rational players who maximize their personal rewards. The Chicago School of Economics emphasized monetarism based on rational game theory models of economic behavior. Mutual assured destruction provided a game theory rationalization for the nuclear arms race during the Cold War. In 1970, Nathan Leites and Charles Wolfe argued that people make rational decisions, so authorities should define the costs and benefits to motivate people in society to behave in desired ways. Leites and Wolfe's ideas were used to justify draconian punishments when attempting to solve the political problems in Northern Ireland and to deter crime in the U.S. with three strikes laws. Sometimes, such as with mutual assured destruction, treating people as rational seemed to work. Other times, such as with Northern Ireland and three strikes, things went horribly wrong. Behaviorism, motivated by carrots and sticks. Using rewards and punishments to train, educate, and manipulate animals and people has been around for at least thousands of years. Spare the rod and spoil the child is an ancient proverb. In 1937, B.F. Skinner began developing behaviorism, refining the notion that animals can be trained and controlled through rewards and punishments. His ideas were widely adopted by managers. Behaviorists used to think of leadership in similar terms, of motivating workers through carrots and sticks. Susan Fowler notes that Skinnerism seemed to work. Management after World War II was full of gamification, rewarding and punishing workers based on metrics. Quote, complex schemes motivated workers with compensation systems, rewards, contests, tokens, badges, prizes, and formal recognition programs. The SEI fully espouses behaviorism when they use processes and metrics in the CMM and Scampi to judge and motivate programmers. logical, and robotic. Computers affect expectations of who people are and what people should become. In the 1950s, those with a narrow focus on technology were referred to as computerniks, meaning something like idiot savant. In the 1960s, as the prospect of computers and robots loomed, Spock became the ultimate or ideal human being. Spock embodied a hybrid of human and robotic behaviors, fulfilling the dreams of Socrates, Moore, Boole, Putnam, and others of perfectly rational humans. The original Star Trek ran from 1966 to 68 before the public understood what computers are and could do. Autism is now becoming an important ideal in pop culture, for example, in the TV series Elementary and in the book The Curious Incident of the Dog in the Nighttime. Some companies now specifically hire autistic programmers, believing that they provide competitive advantages. Programmers are inconsistent and unreliable. In a deterministic world, people, and especially programmers, are compared with perfection, and they often fail to be as robot-like or as productive or perfect as managers desire. Managers seem to view programmers as lazy and error-prone. Transactional management. In a deterministic world, the division of labor between managers and developers is mainly transactional. Managers give workers paychecks in exchange for bossing them around 40 hours per week. Managers motivate teams and track projects using processes, rules, metrics, carrots and sticks, challenges, money, power, and fear. These practices endure because of tradition, but are justified by rational economics and behaviorism. Managers naturally prefer transactional relationships because it simplifies the work for managers and exaggerates class distinctions between managers and workers. Transactions enable managers to turn their attention away from coaching their teams and toward other duties. It does work. Behaviorism and transactions work for routine assembly line tasks like dishwashing, which tend to pay poorly. Career software engineers work in exchange for salaries, and many top athletes and actors perform best for large prizes and fees. Irrational humanism. In the 1800s and early 1900s, psychology focused primarily on mental illness. But over the last 75 years or so, psychologists and sociologists have begun focusing on normal people. In the 1940s, led by Abraham Maslow, they began asking, how do normal people actually behave? And how can normal people do better work and live better lives? Irrational. People are irrational in many ways. Blind spots. Psychologists have learned that normal people have many cognitive blind spots, including the confirmation, self-serving, and hindsight biases, the gambler's fallacy, and the law of small numbers. The confirmation bias describes the tendency of people to notice data that confirms their beliefs and to ignore data that contradicts their beliefs. So providing better data or examples rarely changes anyone's mind and may even provoke stubbornness. The gambler's fallacy is the belief that in a 50-50 game, wins and losses will even out, so if a gambler keeps playing, he or she will eventually recover from a loss. Most people blatantly misunderstand randomness. The law of small numbers is the belief that small samples actually do represent large populations. These blind spots are part of the brain, and nobody can avoid them completely, not even statisticians and psychologists who should know better. Matthew Hudson argued that these biases were useful in human evolution, but can cause problems in modern society. Charity. Millions of programmers work on open source projects for free. Probably billions of people donate to charity. Charity contradicts all rational economic theory. Behavioral economics. As behavioral economics emerged in the 1980s and 90s, mainstream economists slowly accepted that people make many irrational decisions. Daniel Kahneman and Richard Thaler won the 2002 and 2017 Nobel Prizes in Economics for revealing these irrationalities. Thaler argued that the rational human, or Homo economicus, that John von Neumann presumed occur as rarely as unicorns. Everyone struggles with temptation, causing too many people to fail to exercise and too many to fail to save for retirement. Resisting temptation turns out to be hard work, and people need help doing so. Motivated by autonomy, relatedness, and mastery. Psychologists have learned that people do not primarily maximize their personal rewards, and that people who excel are not primarily driven by greed and fear. Abraham Maslow, Edward Deci, Carol Dweck, Anders Ericsson, and many others showed that intrinsic and peer motivation work much better than extrinsic or manager motivation. Daniel Pink summarized their results with the principles of autonomy, mastery, and purpose, Susan Fowler summarized them as autonomy, relatedness, and competence. It takes all three to excel. Autonomy. People need to have choices, and they need to believe that their work is of their own volition and that they are the cause of their own actions. As a rule, software engineers hate being told how to do their work, just like everyone else. Everyone dislikes rigid processes. Relatedness. Most people like to help and please and work with others. Adults want to produce something of value, to give something back to the world as an act of gratitude. Generativity means giving back and nurturing the young. Developers like to deliver treats to users and get thank yous in return. Workers also want to be part of an effective team, in other words, to have a group of peers who understand and appreciate their efforts. Competence and mastery. People need to feel competent and effective. They want to demonstrate their mastery of skills by working on and solving truly hard problems. Software developers like to build interesting, innovative features and applications. They also dislike feeling stupid when they are thrown curveball tasks or must work on parts of a code base that they don't know. Emotional and human. As PCs and smartphones became widely used throughout society, everyone began to understand that people are not and should not be robots. People are emotional. Increasingly, people realize that software engineers are emotional creatures. Brené Brown argued that vulnerability is the essence of courage and that killing emotional lows also kills emotional highs. So healthy people should experience a broad range of emotions. Software problems, such as struggling with a difficult bug, can lead to disappointment, frustration, and even anger. Finding solutions is fun and builds pride. Successful software engineers must learn to work through their emotional highs and lows. Ideal people. As Spock became understood, everyone realized that humans cannot and should not emulate him. Nobody is as knowledgeable or disciplined as Spock. Nobody can be, and Spock eventually stopped being a human ideal. Enlightened management. In general, enlightened management seems to work much better for sustained productivity, and contemporary software processes increasingly urge enlightened management. Enlightened management combines a lot of good ideas. Bertrand Meyer argued that, quote, guru managers should establish a productive environment, champion the team, and handle resources. Both large-scale Scrum and disciplined Agile delivery encourage teams to have coaches rather than bosses. Desi Brown argued that leaders should tell stories to workers to explain why their efforts matter. We believe that truer stories work better. Daniel Kahneman argued that leaders should generally express more praise than criticism to workers because of the regression to mean illusion. In Management 3.0, Jürgen Appello provides many suggestions about motivations, purpose, and communication. Unfortunately, in our opinion, enlightened management remains a poorly defined and ad hoc collection of ideas, and it remains far from clear what guru managers should actually do. We believe that enlightened management is not yet a coherent and teachable concept. This makes sense because a finite number of enlightened rules cannot cover the infinite possibilities that could arise. In our experience, most managers still seem lost without their carrots and sticks and action items and spreadsheets, and enlightened management remains far from the norm. Note that happy programmers can still write bad software, but surely unhappy programmers would write worse software. Note that we mean happy in their work rather than happy-go-lucky. And note that humanism is not quite the right word, but we have not found a better one. Both. In general, software engineers need both some rational behaviorism and some irrational humanism. Rational behaviorism. Software engineers pride themselves on being rational, especially whenever they puzzle out complex software logic or fix bugs. Not every task is inspiring or motivating, and yet they all must get done. So managers must often assign unpleasant tasks to someone, even though that contradicts autonomy and may make the selected individuals feel picked on. And workers need salaries. Irrational humanism. On the other hand, behaviorism and transactions demotivate and demoralize most people. Managers should evoke autonomy, relatedness, and mastery whenever possible. For example, daily stand-up meetings encourage developers to make personal commitments to colleagues and provide opportunities to share their challenges and victories with their peers. Yet how best to combine rational behaviorism with irrational humanism remains unclear. Giving commands reduces autonomy, but we don't know how managers can direct work without giving at least some commands. Merely mentioning money lowers productivity, but we don't know how managers can pay workers without ever discussing money. The defined processes and coding standards that organizations impose can raise the level of quality, even though they also undermine volition. Of course, many other social conventions, like wearing clothes, both have benefits and undermine volition.